Hi guys, welcome to CodeDrift Day 5. So the first question we have is saving Gotham, where we are given an array of n elements, and there's a special kind of an operation when we can do it infinite number of times, and by doing that operation we have to make all the elements equal to 0. So in one operation what we can do is we can select two different numbers in the array, and such that the AND value, let's say we select AI and AJ. So if the AND value of AI and AJ is X, then we can just replace AI with AI XOR X and AJ with AJ XOR X. So we can do this operation any number of times. So we have to find out if we can make all the elements equal to 0 or not. So let's take an example. Let's say this is the array that we've got. So here I've written all the binary representations of the numbers of the array 2 3 4 5. So let's try to do the operation on 2 and 3 once. So what is the value of 2 and 3? Value of 2 and 3 is 2. Now 2 will be replaced by 2 XOR 2, which is 0, and 3 will be replaced by 3 XOR 2, which is 1. Okay, so the updated array is 0 1 4 5. Okay, now let's try to do the operations on 4 and 5. Okay, so this is the updated array. Now let's try to do the operation on 4 and 5. So 4 and 5 gives us 4. Now 4 will be replaced by 4 XOR 4, which is 0, and 5 will be replaced by 5 XOR 4, which is 1. Now what is the updated array? So the updated array is 0 1 0 1. Okay, now we can do the same operation on 1 and 1. So 1 and 1 is 1. So the first one will be replaced by 1 XOR 1, which is 0. And then the second one will also be replaced by 1 XOR 1, which is again 0. So the array becomes 0 0 0 0. So how do you think we can find out if we can make the elements 0 or not? So the brute force solution which comes to our mind is just perform the operation on every pair possible in the array. So the number of pairs in any array of size n are n square. So we can for every n square pairs, we can perform the operation and find out at the end of all the operations if the elements have become 0 or not. But the what's the time complexity of that method? Since we are doing the operation n square times, so the time complexity would be of n square. So can we do better than that? So if we need to observe what is happening when we are performing an operation on two numbers. So when we performed an action, operation on 2 and 3, in this case, so 2 was we were able to make 2 as 0, but the 3 was transformed into 1. So if we look at the binary representations of 2 and 3, only these bits, this bit right here, we were able to destroy it because it existed in both the numbers. But this bit did not get destroyed in 3. Why? Because it did not exist in the other number, which was 2. So the observation here is in this operation only those bits which exist in both the numbers, they get destroyed, and all the other bits stay as they are. Okay, so what do you think? Let's suppose there's a bit which exists in only one number in the array. Do you think we will ever be able to destroy it if no other number carries it? Let's take an example. Where the array just has two numbers, 4 and 8. Okay, so the binary representation of 4 is 0 1 0 1. This is 4, and the binary representation of 8 is 1 0 0 0, right? Okay, so 4 is 0 1 0 0 and 8 is 1 0 0 0, right? So do you think we will ever be able to destroy these bits no matter how many operations we use? No, because this bit will never be paired with other such bit of the same value, because we don't have any other bit of the same value in any other number, because the only other number we have is 8, and it does not have this bit. And in 8 we have this bit as set, but 4 doesn't have this bit, because this bit is in 4 is 0. So we'll never be able to destroy these bits. So the thing we can notice by this operation is that only those bits which exist in pairs can be destroyed by these operations. So let's say there are many numbers. Let's say this is the number a, b, c, d. Let me just write random binary notations. Let's say this is 1 1, this is 0 1 1 1, this is 1 0 0 0, this is 1 1 1 1. Okay, so let's talk about this particular bit. Okay, so this bit is coming 3 number of times. So I think we can destroy these two, because these two make a pair. But after performing operation on these two numbers c and d, both these bits will be destroyed, but this bit will never be able to get destroyed, because we won't be able to pair it with any other number which contains this bit, right? So the answer for this test case will be no, because we will not be able to ever destroy this particular bit. So we can notice that for every bit, the count of that bit should be even, so that we can divide those bits in pairs of 2 and we can destroy them, right? But if the count of any bit is odd, then we won't be able to destroy that particular bit, and all the numbers will not be able to be reduced to 0 at the end, right? So how can we implement this? So let's see. We can just take an integer array, bits of size 32, and just set it to 0 in the beginning. And then let's say we are given an array a. Okay, so for all the elements, for each x in a, let's say the given array is called a. Okay, so for every number we will check from I is equals to 0 to 32 if x right shift I and 1, we will increment bits of I by 1. Okay, so what is this piece of code doing? So what this is doing is, when we right shift any number by 2 or 1, so what it does is, let's say the binary notation of x is 1 0 1 1 0. So what happens when I right shift? So this operator is called right shift. What happens when I right shift the number two times? So the extreme right 2 bits will get dumped, and all the bits on the left side will just get shifted to the right. So the updated notation will be 0 0 1 0 1. So why do we use right shift? So let's say we have to access the third bit of the number from the right. So we'll just right shift the number 2 times, so that the third bit will come to the extreme end, right? And then we'll just take the and of the number with 1. That will just tell me whether that particular bit is set or not. Okay, so I need to check for all the bits from 0 to 32, since all the numbers are not going to be more than 2 raised to power 32, which is 10 raised to the power 9 in this case. So this is enough. So I'll just with this for loop, I can just count the number of bits in every number. So after this, I have the count of all the bits. Now in the bits array, for int 0 to 32, if bits of I, int I is equals to 0 to 32. If bits I percentage 2 equal to 1, right? That means the count is odd. We will just return false, right? And after the array, if no count was found to be odd, at the end we'll just return true. Okay, so what is the time complexity of this method? Let's see. Okay, so since we are only iterating over the array once, that will make the time complexity of on, plus then after that we are just iterating over the array of size 32, that is a constant time, that will make up on. And the space complexity, since we are just using extra space of size 32, we can consider it constant space, on space. So this is the time and space complexity of the method. So I hope this was clear, and thank you for watching. So I hope this cleared you out. Let's move to the second question. Hi guys. So the second question for the day is loudspeaker. We are given a graph which has A cities and few roads, which are represented by the array B. Array B contains all the edges, right? Telling us which node is connected to which node. And then we have an array which tells us that some cities have loudspeakers. So all the cities which have loudspeakers are in the array C. Okay, and then we have a source city and a destination city. So let's take an example. Let's say this is a graph. Okay, so let's say we have two cities which have speakers, and then let's say this is the source city and this is the destination city. Okay, so what happens is in the beginning this speaker is all turned on, the sound starts traveling. Let's say, okay, so the speaker has an intensity of, let's say the intensity is x, so the sound will only travel up to a distance of x. Let's say x is 2, so it sound will travel to distance in this path, to direction in this path, right? And then it will stop here. But when the sound hits another speaker, the that speaker also gets turned on. So what will happen is this will also start emitting sound, and since x is equal to 2, this will also cover a path of 2, and that means the sound will reach E. So the answer will be yes. For intensity 2, this sound will reach from this source to this destination, right? So we have to find the minimum intensity for which this can happen. So the minimum intensity for a speaker can be 0. The maximum intensity we can be n. It cannot, we will never need intensity more than n, right? If we cannot do it in n intensity, then we cannot do it at all, because the shortest distance from any node to any other node cannot be more than n, because we have n number of nodes, right? So this is the range for our answer. So one way is to iterate from 0 to n, and the first value for which it can be done, it will be the answer, right? But instead of doing that, since it takes on time, what we can do is we can use binary search in this range, and it will give us the value in log n, right? But for every intensity, how do we check if for that particular intensity we can this is possible or not? So we will binary search between this range, and for every value we'll call a function solve with the intensity. We'll send it the intensity, and it will return a value whether it's possible or not. Okay, so how will that function work? So what we can do is since all of these speakers can be sources for the sound, we can use a multi-source BFS, and we can consider all of these speakers to be different sets, right? Let's call this to be set 1. Let's call this to be set 2. So all the cities which can be reached from this speaker will be in the set 1. All the cities which can be reached from this speaker will be set 2. And if some city collides, that means this sound is reaching from here also, and this sound is reaching here, both the cities. So we will check if the distance between this speaker and this speaker is less than equal to x. What does that mean? That means if a sound ever starts from this speaker, it will reach this speaker as well, and eventually this speaker will also get turned on, and the all the cities that this speaker is connected to will also be reached. So what this will do is, what we can do is, we can just combine both these sets. So we'll just, at the beginning, all these speakers will have different sets, and after the BFS, some speakers will be connected, their sets will be connected. What that will mean is that all of these speakers are interconnected. That means the distance between them is less than equal to x, and they can be reached from any speaker to the another speaker, right? So no matter from which speaker we start, we can always go to some other speaker, and eventually some node which can be reached from that speaker, right? So we'll just do a DFS. At the end, we will check if the source node and the destination node are in the same set, right? So how do we make sets? So we can use DSU. So let me just give you a brief explanation of how DSU works, right? So let's say we have a few nodes, 1 2 3 4, and let's say 4 and 5 are connected, right? Let's say all of these nodes are islands and these are bridges. So if I say 3 and I am making a bridge between 3 and 5, so automatically 3 is connected to all the elements which are connected to 5, right? Because if I can travel from island 3 to 5, I can also travel from 3 to 4. If there was a element 6 connected to 5, I could also travel from 3 to 6. So what we do in DSU is, if any element of one set gets connected to any element of another set, that means both these sets are now connected, and now we have gotten a new set, right? So for knowing how we can do these unions and how we can check if the two elements are in the same set or not, you can read more about DSU, right? So now we will look at the code, how we can implement this.
Okay, so this is the function solve. Okay, it takes the vector p, which is the edges, right? This is the vector c, which is the all the nodes which have loudspeakers. This is the source, and this is the destination, right? So what we do is we make a graph, and then just make the graph using the edges, right? And then what I do is, for all the nodes which have speakers, I just insert them into a set so that later on it's easier to check if some particular node has speaker or not, right? And then what I do is I just set the constraints, low as 1 and high as 1 10 to the power 5. So you can either set high to n, or I'm just taking the worst case here. Since n goes up to 10 raised to power 5, I just set it to 10 to the power 5, right? Also, I've set answer to int max. You can also set it to n or the maximum value, right? Then we start the binary search. While low is less than equal to high, we calculate the mid, and then for that particular mid, call this function can do and see if it's true or not. If it is true, we set answer as mid. That means this mid value is our potential. This can be our potential answer if we don't find some value lesser than that, this, right? So we just put this in our answer, and then put high as mid minus 1. That means we are trying to find a better value than this, right? But if it doesn't return yes to us, that means that the sound does not reach the destination with this intensity. So we have to find a bigger intensity. So we'll set low to mid plus 1, right? And then in the end, I just return the answer. If the answer is still equal to int max, that means we never got a value which returned true. That means we have to return minus 1. Otherwise, I'll just return answer, right? So let's take a look at the function can do. So this is the function can do. So this just takes in all the constraints. The mid goes as x. So x is the intensity for which we are checking, right? This is the graph, this is the set. These are the source and destination. And what's n? N is just a, right? The number of nodes, right? So then this parent size, these are just the arrays that we need to make for DSU. So these are the functions is equal and union. These are the functions which we use to this union. Basically, we need this function to make two elements, unite two elements, make them, bring them into a same set, right? We just make this loop to reach the root node of A. We use this loop to reach the root node of B. C, if they are equal, that means they're already in the same set. We don't need to do anything. If they are not, we just combine them, right? You can read more about this, why we are doing this. This is just to make the tree balanced so that the search happens in log n time, right? And this tells us if the two elements are in the same set or not. So we just travel to travel to root of D. If they are equal, they're in the same set, otherwise they're not, right? Okay. So in the can do function, what we do is we just perform the BFS, and then we perform the function is equal. Set D, set E are the sets in which D and E lie. And this is the, we are passing the parent array to check if they are in the same set or not. So what does BFS do, right? That's the main thing. So what we do is we create a array distance. So this is just to, we just initialize it by distance I is equal to -1. That means all the nodes which are not yet visited, we have set the distance to -1, right? And since we are starting from all the sources, which are the speakers, we are doing a multi-source BFS. So for all the sources which have all the nodes which have speakers, I set distance I equal to 0. Since we earlier talked about how starting from all the speakers will be equivalent if those speakers can be reached from the destination speaker, right? So in the end, if all the speakers that will be in the same set as D, we will know that these speakers can be reached by the speaker D, right? And then we can just see if D and E are in the same set, right? So this is what we are doing. This we are just setting the distance of every I, which is the speaker, to 0, right? And then we are assigning some sets to these nodes. Set of I is equal to j plus plus. So we just start j with 1, and we do j plus plus. So just numbering from 1 to, we just keep increasing it and keep assigning a different set to every node which has a speaker, right? Then we just start the DFS for every element in the front. What we do is, if we'll come to this in a second, but so what we do is for all the elements that are connected to T is the element in the front of Q, right? So all the elements which are connected to T, if distance of JJ, which is the element which is connected, is equal to -1, that means it has not been visited yet. So what I'll do is I'll just add that to my set. So I will just assign the set of JJ to set of T. That means that element and the speaker we have started from, which is the T, we just put them in the same set, right? And then distance of JJ is distance of T plus 1. This is very logical. The distance will just keep increasing by 1. And then I just push JJ to the backside, right? This is how BFS works, right? So in the else condition, which means if distance of JJ is not equal to -1, that means JJ has already been visited before, right? So if it has been visited, distance of J must be some positive value. It means it has been visited from some other speaker, right? So we'll just check if this set and this set can be joined together. For that, the distance between the speaker from which JJ has been visited and the speaker from which T has been visited, the distance between them must be less than equal to X, right? That's only when these two speakers can be in the same set, right? So we just check. This is the distance till T. And since we are going one step further, we add 1 to it. And the distance which was already covered to reach J, this is the total distance between the two speakers. If this is less than equal to X, what we do is we just unite the set that T belongs to. That means the speaker from which we have reached T, the set which JJ belongs to. That means the set of the speaker from which JJ was previously uh, reached, right? And then we just unite them, put them in the same set, right? Yeah, we just keep doing this for all the elements, and in the end, we just check in the can do function if T, the set of T, and the set of E are connected. If they are, that means the sound will travel from D to E, right?
So now let's see what the time complexity of this program is. Okay, so we are performing a binary search from 0 to n, right? And for every query, we call the function solve for that particular mid value, right? So in the function solve, we perform a BFS, and there are n elements, n nodes, and since we don't revisit any node, only we will visit n nodes in total. For every node, we use that query union set, where we attach this every node to some particular set from whichever speaker it has been visited, right? And that query takes up log n time, right? And the function and the binary search takes log n time too, which makes total time complexity n log square n, right? Talking about space complexity, in DSU we are using 3 linear arrays, so that makes the time complexity linear. And for the BFS also, we use a queue, which will we will push n nodes in the queue, that will take up linear memory as well, right? So the overall space complexity is also linear, which is O of n, right? So when we were using DSU for the queries, we can also use you can read more about it, about DSU, and read more about path compression. We could have used path compression and made this login factor as O1, but we don't need it in for this question. But if you want, you can read more about it and try to optimize the solution from n log square n to n log n, right? So I hope this solution was clear. Do like the video, share the video, and consider subscribing to the channel for more content like this. Thank you for watching.